In this video we'll continue looking at the system call integrity layer to detect malware using vectored exception handling squared. In a nutshell, this technique involves setting hardware breakpoints over the address, which the malware developer wishes to avoid having executed. The clever thing with this technique is that it occurs in a far more subtle way, where the adversary is able to set the debug register from an ordinary exception rather than through the normal APIs, which are easily monitored by EDRs. I published a blog post on detecting this from within kernel mode, in which we enumerated all threads to look for any debug registers in use by a thread. The drawback of this is that it relied upon undocumented APIs which are not officially supported or guaranteed to work in production. This is clearly a drawback for EDR vendors. In my research at the time, I called out the fact that an EDR could potentially use inline function hooking within NTDLL on NT-continue to potentially inspect the context record. This is because, and credit to CrowdStrike for publishing the internals of exception handling, at the end of any exception being handled, NT-continue is called. When we look at the prototype for NT-continue, we see the first argument is a pointer to the context. Under vectored exception handling squared, as the malware has just set a debug register under the pretense of an exception, we can use the fact that the program will call NT-continue after the event to see whether the context contains a debug register. We can then check whether this debug register points to a function, or any memory region, that we would consider unlikely for a legitimate developer to want to set a hardware breakpoint on. For example, malware which would want to avoid the anti-malware scanning interface from scanning some buffer, they would set a breakpoint on anti-scan buffer. The system call integrity layer is a project I'm working on where I'm building a small subsystem to allow endpoint security vendors to intercept system calls without needing to hook NTDLL. Let's put the components together we need to make this work. First of all, we need to define what a context looks like. Luckily, we can grab the prototype from the Microsoft documentation and recreate this in Rust. We don't need the full record, so we can read only up to where we care about. Next, we need to extend the NT function enum to include NT-continue, which contains an invariant which will allow us to easily express data held within the enum. In this case, we want to pass the partial context as well as a signal, which we'll be using the driver to look up, which indicates whether a debug register was pointing to an address that is indicative of malware. In our case, we're using AMSI scan buffer to try bypass AMSI. Now we need to go into the driver code, which of course is built in Rust, and in the kernel system call hook mechanism, we can prepare the data to be sent up to the EDR. Here we can attach our thread to the process's address space and read what was in that first argument passed to NT-continue, which as we now know is a pointer to the context. After reading the context, we check whether any of the debug registers are in use. If they are, we check these against a list of known APIs which malware uses to evade EDR. If we detect abuse, we set the enum invariant to contain the partial context as well as information as to which function the potentially malicious program was trying to avoid having executed. Then in the user mode component, we can read the data we sent out of the driver, and if the driver has detected abuse of an API, the EDR can then go ahead and handle it. The idea of the system call integrity layer is that this could be an officially supported API that Microsoft could put into Windows 11 for EDRs to monitor system calls without needing to be in the kernel, or from hooking NTDLL, which malware can easily bypass. So let's take a look at this in action. Okay, so we're in the VM where we're going to do the testing, and you can see we have the driver, we have the engine, and we have the test binary. So the test binary is going to emulate the malware here, and it's going to use vectored exception handling squared to set the vectored exception handler on AMSI scan buffer. After doing so, we're going to go ahead and call AMSI scan buffer directly, simulating the operating system running AMSI scan buffer on perhaps, say, a .NET executable which is being run in memory. What we'll see when we run this the first time is the function, or the program I should say, executes fully and we get to the finished print, so that means that the vectored exception handler did work. Secondly, we'll then run it with the driver and the engine turned on, And what you'll see there is the system call integrity layer essentially interrupts the process, and it detects, hopefully, the abuse of vectored exception handling on a sensitive API such as AMSI scan buffer. So without further ado, let's go and run the test binary first with everything turned off. And as you can see, we've got to the finished print, and we printed the part of the program where we are in the vectored exception handler, which would then prevent the AMSI scan buffer from running. So if we kill that and we go ahead and we'll start the driver and we'll run the engine like so. And we can then run the test binary again. What we see this time is we do print the context address in the console, but then we don't get any further forwards, so we don't actually get the callback to the vectored exception handler. Instead, what we see in the engine is it prints malware detected using vectored exception handling to bypass execution of security intrinsic AMSI scan buffer. So the system call integrity layer has essentially allowed for the EDR to hook the NT-continue part of the the sequence of events which must take place for vectored exception handling to be abused, and we have detected that it had set a debug register on AMSI scan buffer, which is very indicative of malware. So the EDR, the logic, the system call integrity layer, thumbs up, it's detected the technique. If you like this content, please be sure to subscribe, like the video, share it around. If you want to see more content like this, then hopefully I'll have some more for you coming very soon. Until next time, peace out.